super excited about being a part of it. And I appreciate the two speakers in the last 2 weeks for setting the table for me so nicely so that I can talk about the things I'm most excited about, but I'll also do a little bit of review for the new folks in case this is the first time you're joining the seminar. I have no idea how long these slides will take me. I just thought, prepared what I thought was the right amount to say, but I hope we'll have time for discussion throughout. And I don't really have an agenda, so I welcome people to stop me with questions throughout. Slava, I hope you'll keep an eye on the chat for me as I go and interrupt me also if people record questions in the chat. And last but not least, I have to go to a swimming lesson after this. So if I don't get time to talk to you in GatherTown afterwards, then please send me email or follow up with me in later weeks of the workshop to talk about questions or ideas you might have. Yeah, so I wanted to start with an overview of what happened in the first couple weeks so far and maybe what some of the common themes were. I know Alexei Borodin and many of you share my love of Baxter's book, Exactly Solved Models in Statistical Mechanics. You know, I could only rescue a few books from my office before the pandemic started, and this is one of the ones that I rescued from my office to have at my bedside. And already, if you look in Baxter's Exactly Solved Models book, you'll see all these different ways of talking about lattice models. So we have spins here, we have arrows, we have particles, and we have paths. And for most of the day, I'm going to be talking about the 6-vertex model or generalizations of the 6-vertex model. And so there, it might be a particular choice of 6 possible spins around any particular vertex in this rectangular lattice, or it might be the choice of particles and holes situated on the edges of the lattice, and so on and so forth. But whether you choose spins or arrows or particles or paths, according to Baxter, all of them come with slightly different ways of thinking, but the game is always the same. The game is, I give you some boundary conditions and some Boltzmann weights on the vertices, and then we try to evaluate the partition function. The partition function is given as a sum over all the admissible fillings, and then for each admissible filling, we take the Boltzmann weight of the state, which is a product of the local Boltzmann weights. I think, having looked through the crowd on previous workshop days, I'm saying things that are extremely familiar to all of you so far and that were covered in the first 2 lectures. But like I said, if you have any questions, stop me. But what I find a particularly interesting direction is the opposite direction. So for me, what's most interesting is to choose my favorite special function. And my favorite special function, depending on what day it is, might come from complex geometry or Schubert calculus. It might come from the representation theory of p-adic groups. It certainly would not come from probability, but I hear that that can be done. So if your favorite special function comes from one of those sources, then the goal is to try to construct a lattice model made from boundary conditions and Boltzmann weights whose partition function matches your special function. Or better yet, a family of special functions that can be rendered as a family of lattice models. Okay, so in pictures, what that might look like is, you know, if we use the arrow version of the 6-vertex model, we could put some collection of up and down arrows along the top row, and we could record that position of those up and down arrows by a partition, as we saw in Amol's talk last week, for example. We could record some random collection of up and down arrows as a partition along the bottom edge. In practice, it seems to give better results if you make the things boring on both sides. Some random collection of ins and outs along the edges doesn't seem to work so well. And then we try to solve for the partition function. So in this way, I want you to think of the partition function as dependent on the boundary conditions and the weights. So the result is some partition function which is currently undernotated by p lambda mu. Lambda and mu are my two partitions. Okay, so I hope this is all very familiar to you, but now I want to talk about the particular bells and whistles that we can add to this partition function. So the first bells and whistles we can add is that we can allow the Boltzmann weights to not just be independent complex constants, but rather to depend on some parameters that we associate to each row and column. So for example, I could associate some complex parameters x1 through xr to the rows, and I could associate some parameters y1, I guess I wrote yt, on the columns, and then the Boltzmann weights could depend on x and y in some way. So I've indicated this here in the weight by a new parameter z that depends in some way on some binary operation, which I've written as this big O plus in LaTeX. Okay, and so if we put this all together, then now we want to write these functions as dependent on these parameters z. Okay, so my output is some special function in two sets of variables x and y. And I wrote it as big O plus because it's actually quite interesting to allow that binary operation to be a formal group law. So the different formal group laws are things like the additive group, the multiplicative group, or say the formal group associated to an elliptic curve. And there's some really interesting work by, well, I like this paper of Korf and Gorbunov, where they explain that if you vary the formal group in a particular set of Boltzmann weights, you actually get the corresponding cohomology theory for the corresponding flag variety in your lattice model. So if you use the additive group, you get ordinary cohomology. If you use the multiplicative group, you get K theory. If you use the elliptic curves formal group, you get some version of elliptic cohomology. And so there's this beautiful way in which the lattice model is somehow smart enough to understand that when you replace these Boltzmann weights by these different additive group laws, you get these different geometric interpretations. That's just one example of the way in which lattice models are miraculous, that they seem to encode much more than we would think from first glance. Okay, so that's one bell and whistle we can add. We can add variables. What else can we do? So the other thing we can do, and I'm not going to talk too much about this today. In fact, if you're excited about the thing I'm going to talk about now, you should pay attention to Henrik's talk the next time it's p-adic representation theory's turn 2 weeks from now in the seminar. But another thing you can do is you can allow your edge decorations to be colored. So instead of having an arrow decoration in a particular orientation, you could allow, for example, n colors to be associated to that and give different weights depending on the different colors that you attach to each of these. Similarly, you could take the arrow pointing in the other direction and attach colors to it. But if you're Dan or Henrik or Valentin or me, you choose to give those a different name to emphasize that they're playing a different role in the model. So instead of colors, we often refer to those somewhat ridiculously as scolars or supercolors. But Henrik is a physicist and he said it was okay. So in any case, there are these ways to take these weights in the 6-vertex model or these admissible decorations in the 6-vertex model and sort of explode them into these many more possible admissible configurations. And that's the notion of color. And Henrik's going to talk a lot about the effect of color, but I'll say a tiny bit more about it today. And so now, instead of having just a partition, to describe your top boundary, if you also allow the parts to be colored, then you invoke permutations. And so you can mix permutations and partitions and get even more interesting statistics written as compositions, or if you're a representation theorist, you might think of them as weights, just elements of z to the r, because now instead of having an ordered collection of integers, you can scramble them using the partition. Okay, so the upshot of this, and somehow toward the end of the conclusion of the review here, is that if you put 1 and 2 together, our partition functions are these multivariate functions which are indexed, unfortunately, by these combinatorial partitions. It has nothing to do with the word partition function, or they're indexed by permutations, or they're indexed by compositions. And I think one thing that unites many of the people in the audience is that our favorite special functions are indeed indexed exactly by this kind of data. Okay. So the last bit of review is just to remind you here in the first few minutes about how you prove that if you're given a set of weights and boundary conditions, that you got your favorite special function, you got your desired partition function. And that's where solvability comes in. So recall just very briefly that solvability, or the Yang-Baxter equation, can be phrased in terms of these two pictures. That is, I've got these two mini partition functions on either side, and I'm asking for a new set of weights that I'll call the R matrix for algebraic reasons, that allows for this equality to be true as I vary over any choice of the 6 boundary edges on either side. So I copy and recopy the choice of 6 boundary decorations on each side, and then I ask for a new set of weights that make these mini partition functions true. Okay, and notice that the spectral parameters on either side here reverse roles. Okay, so this is telling me some sort of relation on my partition function when I perform the interchange xi goes to xi plus 1. And maybe we didn't talk so much about this in the first couple of weeks, but it tends to be the case that these R matrices satisfy these additional relations. One of them is this Braid relation, which I've depicted in this not so well drawn diagram here, which says that if we do 3 of these R vertices in a row in either order, we get the same result. And the other relation that it satisfies is that if I do this R matrix twice, being careful about the order in which the spectral parameters go, I get this, I get some expression for doing it twice, which I can think of as a quadratic relation. And so when I put this all together, what we're saying is that solvability, when it works, is giving us some kind of action of a Hecke algebra on our partition function. Okay, so it's a symmetric action in as xi and xi plus 1 are interchanged that satisfies the Braid relation and the quadratic relation. Okay, so just to kind of drill down on this more, there's a really nice old paper of Fomin and Kirilov on Hecke algebras and the Yang-Baxter equation. And in particular, in that paper, I wish I had recorded the title. Maybe some enterprising audience member can write down the title in the chat for me of the Fomin and Kirilov paper. But they define these Hecke algebras, which are totally natural from a combinatorial point of view, that depend on these 2 parameters, depending on the quadratic relation. Okay, so here I've written ti squared is a ti plus b, and we're going to denote the Hecke algebra by HAB. And so there's a particular choice of A and B that a representation theorist would love, namely the Hecke algebra that corresponds to certain functions on double cosets. But there's nothing stopping us from considering these arbitrary Hecke algebras with these arbitrary quadratic relations. And if we go back to the quadratic relation as I wrote it, well, here I was stipulating a particular kind of quadratic relation where when I do these things twice, I get a constant. I guess I I wouldn't out of hand dismiss other types of quadratic relations that allowed for non-trivial A's and B's, but at least as I wrote it on the slide here, you can see that this diagram too corresponds to setting A to be 0. The linear term in the quadratic relation is gone. Okay. And in particular, there's a very simple Hecke algebra H01, which is just the group algebra of the corresponding symmetric group, the Weil group in this case. But H0B is potentially more interesting. Okay, so to sort of conclude the review, the upshot is just to say that if you want to study special functions, you can, that you know have a Hecke algebra action on them, you can use solvable lattice models. Or you could consider using solvable lattice models to try to represent such functions. So in the simplest case, I'm just saying if you have your favorite symmetric function, a symmetric function is an example of a function that's invariant under the H01 Hecke algebra. And so you might try to study symmetric functions using lattice models. But more generally, you might have any old Hecke algebra with these parameters, and you might try to study those functions that have some natural Hecke algebra action using a partition function. And to say a tiny bit about this uncolored and colored models, the way we tend to think about it is that the uncolored models give us symmetric functions, and when we refine them to colored models, they give us non-symmetric counterparts. So if you had a Macdonald polynomial represented by your uncolored model, you might hope to get non-symmetric Macdonald polynomials in their colored model counterparts. Or if you had some specialization of Macdonald polynomials, you'd hope to get the non-symmetric specialization in the colored model. This is a point of view that was really hammered home to us in a paper several years ago by Borodin and Wheeler, the first sort of use of color that demonstrated this to us. Maybe it was known in other contexts before. But this was really eye-opening for us as representation theorists, because we have very natural ways to pass from symmetric functions to their non-symmetric counterparts. That is, we can take the k-fixed vectors in a representation where k is this maximal compact group. So this is a natural thing to study in p-adic representation theory, vectors in the representation that are fixed by a maximal compact group. And then you might try to refine that to an even smaller compact group called the Iwahori subgroup. I'm not going to tell you what it is. I'm just going to tell you that its double cosets give a partitioning of that maximal compact group over the permutations, over the elements of the Weil group. Okay, so just in the way we said before, as we go from uncolored models to colored models, we introduce permutations. And on the representation theory side, we can see that as moving from k-fixed vectors to Iwahori fixed vectors, again, parameterized by Weil group elements or permutations. All right. I thought that saying too much about p-adic representation theory is the wrong thing to say in this crowd, because I thought maybe people were more interested in what unites us rather than the things that are specific to our particular domains. But this slide is an exception. I wanted to say a tiny little bit about p-adic representation theory. I said before that there are these Hecke algebras that are natural in the context of representation theory. And in this case, one such natural Hecke algebra is from this space of functions on double cosets. Here I put just the maximal compact. You could put the whole group there and get an interesting Hecke algebra too. But here I'm looking at I double cosets in the maximal compact. And again, this turns out to be isomorphic to the finite Hecke algebra, where the quadratic relation is given in this way. So my A and my B from before in this HAB are now this particular quadratic relation's parameters Q minus 1 and Q. And you say, well, that wasn't in your list from before. You said before that the Hecke algebras we study are H0B in the context of this lattice model. And here in the context of p-adic representation theory, It's not that. You have q minus 1 and q. So what gives? And the point is, yes, it's true. It's not of the form that I described above, but of course I could just take some affine linear transformation on the Hecke algebra, and I could transform it into some new operators, and those new operators would be of the form that I talked about before. They have a quadratic relation such that their square is an honest constant. In other words, I could kill the linear term by a change of variables in the quadratic relation. You believe me because you've all been in 7th grade where we've messed around with quadratic equations and you've done this very thing. So what happens in that context? What is that A that results from doing that process? You had a Hecke algebra operator and now you turned it into some new operator A whose square is a constant. Well, it turns out that A, if you follow through all the details about what you have to do, is totally natural from p-adic representation theory. It turns out to be something called a standard intertwiner of a principal series representation. And so for the representation theorists out there, this is why it turns out that the lattice model is so effective for studying p-adic representation theories, because the natural intertwining operator from representation theory indeed satisfies this beautiful relation. Its square is a constant, just like you expect from the R matrix, and its braid relations are satisfied. Okay, so we could just boil all this down to the following slogan: that those R matrices, those things that solve the Yang-Baxter equation, describe actions of intertwining operators when your lattice model deals with p-adic representation theory. Questions so far?
There is a question in the chat, Ben.
Oh, great! Help me out with it.
Yeah, the question is, what is a good reference about the standard intertwiners?
What is a good reference about standard intertwining operators? Well, one place is the papers of Castleman and Schleike, where they're trying to calculate particular special functions called the McDonald zonal spherical function and the Whittaker function, certain invariants made from p-adic representation theory. And there you'll see all these properties of standard intertwining operators described. I guess any source on p-adic representation theory should include some discussion of these standard intertwining operators, since principal series are such a big part of it. Maybe the other place that I'll mention is that there's this lovely paper about Iwahori Hecke algebras by Haynes and Kotwitz and Prasad. And in that paper, they talk about the ways in they will give you, for example, this exact relation. Let's see. I was going to try to actually just pull up the paper on my desktop and come up with the exact reference for the equation number. Is that totally ridiculous? Yeah, so it's equation 1.14.1 in this paper that gives you the exact relationship between the intertwining operators and the Hecke algebras. Other questions? Okay. Great. So if you agree that this is a good thing to do, to try to come up with your favorite special functions with the Hecke algebra action, try to write them as partition functions of solvable lattice models, then how do you use solvability to prove you've got the answer you want? I just wanted to go through this quickly because it brings up some interesting points. One way to do it is to say, well, okay, so solvability gives us a Hecke algebra action. And then we can use this plus a bunch of other axioms to uniquely determine the partition function. And this is the approach that was used, say, like way back when by Izergin and Karapin in the 6-vertex model, or Kuperberg in the proof of the alternating sign matrix conjecture, where other axioms means things like, prove the partition function is a polynomial of bounded degree. And so now it's a polynomial bounded degree and it has these functional equations, so it's uniquely characterized and therefore you have the answer you want. So that's the kind of thing that Dan and Saul Friedberg and I used in our first paper on Yang-Baxter equations and some deformations of the Weil character formula. This is sort of the method we used. And lately, when we've been talking about color, we've been using method 2, which is to pass to a colored refinement of these uncolored models. And then the Yang-Baxter equation, they give these recursions with respect to the length of W, the Weil group. And it allows you to write your final partition function in the uncolored case as a sum of these colored models, which are each themselves given by these certain operators. Those operators turn out to be de Mazur-like divided difference operators. And I think that Henrik is going to spend his lecture 2 weeks from now talking about that method. So I'm not going to belabor that, but just to say that, for example, in a simple 5-vertex case that I won't bore you with the Boltzmann weights about, you can honestly write down a partition function, which is just the usual Schur polynomial, S lambda. And then it's not just de Mazur-like, it is de Mazur exactly that you get as these summands. You get these de Mazur atoms that make up the de Mazur character formula. So a slogan for this method would be that if you pass from uncolored to colored models, it seems to be the case that you can represent your uncolored partition function as the de Mazur character formula, or generalizations or variants of it. You get these operators that are de Mazur-like. I wanted to mention that not just to make you excited about Henrik's talk in 2 weeks, but to contrast it with something that Amol said in his talk last week, which was, if you remember, Amol used solvability at one point to come up with a different expression for the partition function. He called this the algebraic beta ansatz. And my preferred paper on this is a paper of Borodin and Petrov, which starts with the phrase higher spin 6-vertex model and continues on from there. Probably the unique paper of theirs that starts with the phrase higher spin 6-vertex model, but I can't be sure. And the reason I wanted to mention it is because, again, if you use the algebraic beta ansatz, as Amol told us about last time, you get another decomposition, which is a sum over permutations, a sum over elements of the Weil group. But this time around, if you do that, for example, in this like 5-vertex example that I mentioned before for the Schur polynomial, you don't get the de Mazur character formula, you get the Weil character formula. So the Weil character formula, remember, is just this like W action on this row shifted monomial divided by some denominators. I find that very interesting that there are these two methods to evaluate the partition function, and they result in the de Mazur character formula versus the Weil character formula. And I feel like there's more to be explored there. If somebody has sort of smart ideas about that or comments, I would love to hear them at some point. So a lot of this story is based on conversations I've had with my student Katie Weber, who was showing that not just in the 5-vertex case, but also in this 6-vertex generalization, this deformation of the Weil character formula, the algebraic beta ansatz can be used to produce this natural sum over the Weil group. So if you have questions about that, talk to my student Katie Weber, who is regularly attending this seminar about how the algebraic beta ansatz precipitates the Weil character formula. Okay, so those are 3 ways in which I know how to use the Yang-Baxter equation to actually do this thing of proving you have your favorite special function. But I also wanted to mention that there are these Hamiltonian methods as well, where now we go back to the first slide where Baxter told us all the ways to think about the 6-vertex model. And instead of thinking about arrows, we think about particles and holes. And so now you might have your favorite partition lambda as the presence of particles in certain columns, like in column, well, this is way too fat a pen to be writing this, but you know, in column lambda 1, you have a particle. In column lambda 2, you have a particle, and in column lambda n, you have a particle, and then you indicate the partition that way. And you describe your Boltzmann weights as these rules for this discrete time evolution of your particle system. So you travel from lambda down to mu, and you keep evolving this particle system until you hit some vacuum state, which is, you know, defined by having all the holes to the left of some arbitrary origin and all the particles to the right of that origin, or something like that. I'm being very vague about this, but I just want to indicate to you that this is a different, exciting way to evaluate the partition function, is to think of the partition function as being realized by this Dirac notation bracket, where this Hamiltonian sort of acts on lambda and it spews out all these different states. And then if you pair it against the empty set, that's recording the partition function that evolves you from lambda down to the empty set. And then you could prove once again that your partition function is of the form you desire by proving commutation relations for the resulting Hamiltonians. And none of this, Andy, am I right about this? Andy Hart is another one of my students who thinks about discrete time evolution and Hamiltonian methods. Andy, I never really used the solvability of the model here, right? I'm just using properties of the Hamiltonians. Is that correct?
Yeah, as far as I can tell, yes.
So there seems to be some correlation between solvable lattice weights and being able to do these Hamiltonian methods and prove these commutation relations, but they're not expressly used in the computation. So that's, again, a sort of interesting and funny point about Hamiltonians and solvability that Andy and I are puzzling about a lot right now, and we'd love to hear other people's thoughts on it if you've thought about this problem. Okay. So that's all the ways you can use solvability. I think we sort of maybe touched on some of them in past weeks, but not quite in this way. So I wanted to take the time to do that. Questions? Okay. I hope the question. Oh, go ahead.
Yeah, just have a quick question. The AIs that were some linear combination of the TIs, do they still braid?
Yes. Just you probably know this fact that are
you're right. Yeah.
The standard intertwining operators do braid, but now maybe you've seen this before. They square to some funny thing that looks like a Harsh-Chandra C function product.
Yeah.
Yeah. So that's the identity we're looking for.
For the Hecke algebra, if you just do an affine change of the generators, the braid relations still work, I guess.
Yes.
The linear and the quadratic come together to show that.
Yeah, but the affine change depends on the spectral parameter involved, you know, so it's not like a complex constant, right? It's a function of z, like the Harsh-Chandra C function, you know, this like 1 minus QZ alpha over 1 minus Z alpha kind of thing that pops up everywhere in p-adic representation theory.
Right. Okay, thanks.
Yeah. Other questions? Okay, I hope the question you were asking is so what? Because we were assuming all along that it was a good idea to connect solvable lattice models to our favorite special functions, but I hope the question you're asking now is like, what do we get out of it? What do you learn about about your favorite special function if you can put it on a lattice model? And so what I want to use the last little bit of my talk to explain is the so what. In particular, one thing we get out of this is we obtain all sorts of identities and relations which can be seen to follow from these kind of diagrammatic proofs that I'm going to show you at the end of the talk. So the kinds of rules I have in mind are like Koshi identities or branching rules, but also all these like ready-made generalizations of things you can do when you have a function on a lattice. So if you have a function on a lattice that's a 5-vertex model, you might try to make it into a 6-vertex model. You might try to go from an uncolored model to a colored or a scolored model. You might replace the formal group law with a different formal group law and use all the kind of built-in functoriality that is sort of magic about lattice models in order to extend your results about your favorite special function. And there's even a way to sort of adjust your lattice model geometry, which I'm not going to talk about at all, to handle other Cartan types. So the rectangular lattice geometry that we're mostly dealing with in today's talk should be seen as a general linear group or a type A phenomenon, and there are other Cartan types you can attack with other lattice model geometries. That's also super interesting. So the point is that somehow the identities are formal. If you can put something on a lattice model of a given type, then all this good stuff just comes from all the bells and whistles and formality of the diagram, and not anything else. If you've got a function that can be represented as the partition function of a solvable lattice model. The other thing you can do is that these Yang-Baxter equations, they come in mathematics from a totally different source, or seemingly different source initially, modules for quantum groups. You know, quantum groups were originally invented, as I understand it, by Drinfeld and Jimbo to sort of explain instances of Yang-Baxter equations. And so, you know, every one of these Yang-Baxter equations is associated to a module for a quantum group. And to me, that's the biggest question in this this field for my purposes, is how do I understand what is that quantum group module telling me about my special function? So I'm calling this Brubaker's mittleren Alterstraum, which is Brubaker's middle-age dream, because, you know, some really good mathematicians can dream about complex multiplication when they're young. It can be the dream of their youth, but sort of mediocre mathematicians like me, it takes us to our middle age in order to have a dream. And so this is Brubaker's middle Alterstraum, as opposed to Kroneker's Jungen Traum. And that dream is to create a dictionary between quantum group modules and partition functions. You know, so to create a dictionary that has enough of a kind of functoriality behind it that you can make predictions in either direction. So if you have a favorite special function, you can associate it to a particular quantum group. And if you change the special function in this way, then you'll change the quantum group module in that way. And I'm totally fascinated by this question, and I have no idea how to answer it because I don't have enough examples. But I'm super excited about the possibility of creating this dictionary because I believe it's, whatever the answer is, it's extremely important. So it would be great if the only thing that happened, I mean, it won't be the only thing that happened, but I would already regard it as a win if the only thing that happened in this workshop is I got more examples of quantum group modules that were associated to special functions so that I could sort of help complete this dictionary a little bit more.
So
okay.
If I understand what you're asking, I mean, McDonald polynomials are sort of special. I mean, the work of Naomi and so on explains that McDonald polynomials can be thought of as spherical functions for quantum symmetric spaces.
Okay.
That's kind of, okay, but that's when Q is some power of T, and and the Whittaker story and the Hall Littlewood, that's when one of the parameters has been set to 0.
Yeah.
Okay.
I see.
So
Maybe let me see if I've got where you're going with this, Siddhartha, because you might be like 3 steps ahead of me. You're thinking of sort of the tower of special functions with lowly Schur functions at the bottom and Macdonald polynomials at the very top, and thinking that maybe this dictionary is really just about understanding what a Macdonald polynomial has to do with a quantum group, and then you can sort of get everything in the hierarchy by specializing.
No, I mean, something very precise. So somehow, I don't know. It's my, I guess, middle age or old age dream to understand Macdonald polynomials in sort of in complete generality. And what usually happens is that you can understand this or that limit of Macdonald polynomials quite well.
Yes.
And so Whittaker functions and also p-adic spherical functions or Iwahori and so on. And lots of functions are sort of a 1-parameter specialization.
Yeah.
And quantum groups do show up for Macdonald polynomials, but if you take Q to some, so there's a Q and a T in Macdonald polynomials. Yeah. And if you take one of those parameters to be a power, so you have a quantum symmetric space. There's a theory of quantum symmetric spaces, which are like analogs of, there's one for real complexes and quaternions. And the work of Masatoshi Naomi has shown how to think of Macdonald polynomials as spherical functions for these quantum symmetric spaces. And Gail Letzter has written, Letzter and Joseph have many papers on this also. So I'm just pointing out there is a connection, but it's not on the axis, it's rather on some diagonal line. In the
yeah. This is often the problem, right? Is to somehow come up with some matrix coefficient interpretation of the full Macdonald polynomial in Q and T without having any limit or specialization or.
Yeah, right. Okay, but sorry, I didn't mean to interrupt since you asked.
No. This is exactly what we should be doing in this seminar, is kibitzing like this. So that's great.
Okay, all right.
Other questions, comments? I guess once upon a time I was Googling around the internet and hit on a Math Overflow post that gave this really pretty hierarchy of special functions. I should find it again for the workshop folks, but it sort of talks about this, we all sort of know this hierarchy between sort of Schur functions, lowly Schur functions at the bottom and Macdonald polynomials at top, but it also had tried to situate other things in this context, like Grothendieck polynomials and some other things from Schubert calculus. And, that point of view, I'm not emphasizing much today, but for example, my students and I know some audience members as well, have tried to put other interesting special functions on lattice models. Sylvie, if she's out there somewhere, and her collaborators were writing LLT polynomials on lattice models. And so, it's not all of those fit underneath that Macdonald hierarchy so tidily. So it seems like, more is going on in terms of this dictionary between quantum group modules and cool functions that you can represent. Okay, so I thought I'd just end by talking about like one example of this diagrammatic identity that allows you to use some formalism to prove something about your partition function. And so example 1 is my only example, but I numbered it anyway. And it comes from this paper of Bump, McNamara, and Nakasuji, which is about factorial Schur functions, but you don't have to know what a factorial Schur function is to appreciate the proof. So to just describe it in brief, what one does is you take a partition function for a lattice model like this one, but you see that I've made every single boundary boring. Boring on top, boring on bottom, and boring on the sides. And it turns out that you can evaluate this directly via Yang-Baxter equations. It's not hard to prove that the Yang-Baxter equations allow you to explicitly evaluate this, kind of in the Zergen-Karapin style. Now, that's one way to calculate this partition function. Here's a second way to determine this partition function. The second way is to imagine that instead we make a cut along the middle of this lattice model, and we sort of do this funny thing where we're going to rewrite all the possible things that can show up on the cut. Now remember, I was recording these up and down arrow configurations by a partition lambda, and so I can split this lattice model up into two pieces. So I consider all the possible lambdas that can show up at the cut, and then I have a top partition. I have a partition function that shows up sort of below the cut. So that's this correspondence, the partition function from below the cut. And then I also have a partition function above the cut where what I do to think of it as a partition function of the type I was suggesting before is I take that partition function above the cut and I rewrite it. Is this picture suggestive enough to give you the idea of what's going on in this picture? I take this partition function and I rotate it 180 degrees on the cut so that now all of these up arrows along the top row become down arrows along the bottom row. And this thing, it might not be so easy to sort of figure it out in real time, but this thing becomes something like the conjugate partition associated to lambda when I do this flipping. There's a little bit of complexity there, but I'm giving you the basic idea. So when you cut the partition function in the middle and record all the possible things that can happen at the cut, you've recorded these two partition functions. And now if the weights are chosen appropriately, what you get from this set of, from these two ways of evaluating the partition function is indeed the dual Koshi identity for factorial Schur functions that appears in Bump, McNamara, and Nakasugi for this particular set of weights. So just to remind you, like the dual Koshi identity for Schur polynomials, it's this formula in which this product is what you get by evaluating the first partition function. This is the thing we call the boring partition function. And by evaluating it a second way, we get the sum over all possible cuts of the partition functions from the cuts. Now, in this case, those partition functions turn out to be Schur functions, and so the resulting identity is the dual Koshi identity for Schur polynomials. But in general, this process is completely formal. Anytime you have a partition function on the lattice model that's indexed by these partitions, you can play this cut game, evaluate it in two ways, and get some kind of a dual Koshi identity as a result. And just, to give full credit to Bump, McNamara, and Nakasugi, they're actually doing it in this more complicated case where they've got column parameters that allow them to express certain factorial Schur functions. If you don't know what a factorial Schur function is, that's okay. It's just a double Schubert polynomial. That should clear everything up. But that's just to say that it has some natural cohomological definition. And when we say double in Schubert calculus, we just mean that there's some like T equivariance in the cohomological theory that we're doing. So the double gives some extra torus action by some new set of variables. So that's what Bump and McNamara and Nakasugi do. They prove a dual Koshi identity for factorial Schur functions from this formal procedure. And that's not the only way we could do it. we could do it. There are other formal identities I could talk about, and in particular, some students of mine in last summer's REU were working on a diagrammatic proof of the Koshi identity. And what's interesting about the Koshi identity is that the right-hand side of the Koshi identity is now this product over I and J of something like 1 minus xi yj inverse. And so, that looks like some sort of result of a geometric series. And indeed, the students in the REU were developing some formal proofs based on semi-infinite lattices in order to demonstrate this Koshi identity. So you get these kind of geometric series that come from semi-infinite lattices when you try to produce these formal proofs of Koshi identities as opposed to dual Koshi identities. That's still work in progress. They're finishing up the analysis, but that's how it should go. And I know that Koshi identities were of interest last week because in the Gather Town chat afterwards, we were talking about how Koshi identities are something a number theorist loves because these expressions that you see here that come from the right-hand side of the Koshi identity, they look like the kind of factors you see in an L function. And that's not an accident, that the Koshi identity is a critical piece in certain proofs of facts from automorphic forms about L functions, the kinds of things you could see, for example, in Dan's survey article on the Rankin-Selberg method. And that might be a topic for a later talk in this seminar, is some way about how the Koshi identity kind of plays a role in automorphic forms and L functions, particularly in the Rankin-Selberg method. Okay, I'll stop here and take more questions or comments. Thanks very much for your attention.
Yeah, thank you so much, Ben.